literature review, and then followed by materials we used for this study, and then test protocols that we followed by data analysis, and then uh, life cycle cost analysis. That is part of the project, but we do not have the result of life cycle cost analysis yet, and we also have other objectives, education and outreach, and documentation and reporting. So some of the literature, existing literature, several researchers, they have used commercial nanoclays available. Most of them, they're collocyte, and there are different kind of collocyte, 11, 10A, 10B. Those are pretty much, they are similar, but they have the size of these particles, nanoparticles, they have different size and shape. And majority of them, they have shown that nanoclays, they improve the routing performance, that increases the stiffness. Once you have the higher stiffness value, so that means it is harder. It is going to give you more resistance in routing. So that is majority of the research that they reported. So again, the objective is to see the feasibility of nanoclay. And first thing that it is a kind of a challenging job is to develop a protocol how to blend nanoclay with asphalt binder. Because this is not kind of a traditional liquid or any kind of anti-stiffness, and this is nanoclay. It is monolinite clay. We need some kind of combination of temperature, rotation, as well as the time, how much time we need to spend. So that is one of the objective, was to find a good blending protocol, and then followed by performance properties. And the other objectives are that we want to see the size of and shape of the nanoclay particles. And then, of course, then we want to know what is the optimum doses of that nanoclay. And some of the things that also we need to, we are looking into is the effect of aging, and then perform some chemical analysis, and then followed by life cycle cost analysis. And here are some of the basic properties of the nanoclays used. 3 types of nanoclay we used in this study: collocyte 10A, 11B, 15A, and organic modifiers, so what it is named after, as well as the particle size, density, and intergallery spacing. Intergallery spacing, that is a very important parameter for nanoclay materials. So we looked into a certain range of intergallery spacing property of the nanoclay, and then chemical structures are also provided here. And again, nanoclay, what it is naturally, basically monomoronite. So monomoronite, as you know, that it is silica octahedron and alumina octahedron and silica tetrahedron. So then you have this monomoronite structure. It is usually potassium ion is better if you can modify it with that. Otherwise, in general, monomoronite, it has the H2 ion there. But it has enormous surface energy. Once you have the high surface energy, so that is if you can treat well, and if you can use it, blend it properly, then it is expected to give you better performance properties. And the cost in general, we have found from the literature, if you use polymer, that you need about $80 per ton polymer itself. And if you use nanoclay, that is about $10 per ton. And if you use the bulk amount, like Alibaba, they are selling tons of tons. It is very cheap. And then so it is like there is net savings. So that was the primary motivation of use of nanoclay. And the other thing is that SBS, so SBS or SBR, where does it come from? They come from the refining process, from the refinery as well. So, and those are expensive materials, and they come from the nature. And it has, so it is not like, it is not abundant, but nanoclays could be an alternative materials. So from here, I am going to turn it over to my student colleague, Tariq Morshed, to talk about the rest of the project.
Hello, everyone. This is the blending protocol. Here we try to find out a suitable blending protocol to mix the nanoclay with the asphalt binder. And basically, here we made 8 trial and did the 3 tests. This is the RV test, DSR, and AFM. When we used this 8 trial, we made 2 types of the time use, that is 2 hour and 3 hour. We used 2 types of the rotation, that is 1500 and 2000 RPM, and the temperature is 150 degrees Celsius and 160 degrees Celsius. At the blending protocol, when we did the RV test, here is the first graph. This is the variation of the viscosity at 135 degrees Celsius. Here we used this type of the variation. And we did some viscosity test at 150 degrees Celsius. There is some variation in the viscosity value. This is the DSR graph. Basically, the G star and sin delta value increased when we increase the rotation and temperature and the blending duration. After that, when we rotation 2000 RPM, temperature 150 degrees Celsius, and blending time is 2 hours, are selected because the G star versus sin delta value is nearly same the unmodified binder. And there are we shown some of the AFM value. This is the atomic force microscope for the 2000 RPM and temperature 150 degrees Celsius and blending time 2 hours. The surface morphology was nearly same compared to the neat binder. And here is the deformation. The deformation value is nearly same or the lowest compared to the neat binder. So from this 3 types of the test, we decided that the rotation should be the 2000 RPM, temperature should be the 150 degrees Celsius, and the duration of the blending is 2 hours. After we blending the sample, we did some of the laboratory tests to find out the viscosity. There is the graph. The viscosity is normally higher compared to the neat binder when we mix nanocale with the asphalt binder. At 135 degrees Celsius, the viscosity of the value is increased for 1%, 2%, and 3% colloidite A. And this is the maximum when we mixed 1% 15A nanocale with the asphalt binder. When we mix the nanocale with the asphalt binder, the mixing temperature, compaction temperature is also increased. This is the DSR test. In the DSR test, in the first graph, the log complex shear modulus versus the phase angle, the shear modulus is also increased compared to the time, and the phase angle is decreased. In the other graph, the G star by sin delta value is also increased. This is the viscosity temperature susceptibility. We use DSR data, that is the G star value we used to calculate the VTS value. The first bar is the neat binder, and the other is the nanocale modified binders chart. We also saw that when we mix nanocale with the asphalt binder, the temperature susceptibility reduced. But in the neat binder, the temperature susceptibility is higher. So when we mix nanocale with the asphalt binder, the temperature susceptibility reduced. That is a good result. This is the atomic force microscopy test. At first graph, this is the surface morphology, and basically this is the preliminary result. We want to do some more tests for atomic force microscope. But in the addition value is reduced compared to the neat binder. And addition value is directly correlated with the moisture susceptibility. So this is the good result. And another is the deformation value. This is directly correlated with the rotting resistance. And compared to the neat binder, the nanocale modified binder shows the less deformation compared to the neat binder. There is some of the pictorial picture that we got from the AFM test. This is the surface morphology, DMT modulus, adhesion, and deformation. We want to do some analysis using this graph. And the future work, to complete the project, we need to do some of the work. This is the sessile drop, Texas boiling test, TSR, BBR, creep resistance at low temperature, and also we did some chemical analysis, that is SARA. This is the technology transfer. Using this project, we spread the knowledge of this project. We want to we submit a paper in the Arkansas A State and Arkansas Academy of the Science. And after conducting this test, we can say that viscosity values are significantly increased for nanocale modified binders. Complex shear modulus is also increased, and phase angle is also decreased. Viscosity, temperature, susceptibility parameter significantly decreased for nanocalem modified binders. And the DMT value is increased and deformation and adhesion values is decreased. So it may be said that nanocalem still have a great possibility to become an alternative polymer. This is the acknowledgement. We want to thank Stansted for funding this project. We also want to thank our industry partner, Argonne Industry and Paragon Testing Service, BYK USA, and Arkansas State University. Thank you, everyone.